We're going to call this Unit 3, Lesson 1A for application, because this is the application of Unit 3. So we're going through 5 lessons of application of what we're doing with our logarithms now, what we're doing with our exponential, the kind of cross-blend of what we're doing with them. So this is just like an overview. Okay, so we're looking at logarithmic scales such as Richter scale, pH scale, Bell scale, stuff like that. You know, just a review, and this I'm going to do this because some of you are still not doing well in this part, which is, we got to get that fixed. This right here, solving these, should, to me, be automatic now. Okay, so what I'm saying is that we need to be able to solve for x here. We're going to lose some strategies today to help us get the x's down, but when it's common base, we should be comfortable. Do you understand? So when I see 4 and 2, this right here should be 2 to the 2x, right? Are we okay with that step? And then it should be 2 to the x plus 3. We are now to the easy part, where we say 2x equals x plus 3. The answer is 3. Okay? Like I said, lessons 2 and 3 of the log section is doing this a bunch. And I've seen probably, I'd say 6 or 7 people have been asking me tons of questions on these, which is great. I'm just worried that some of you aren't even touching these. Okay? So this one, okay, 27 is going to be 3 cubed. Okay, so then we're going to say put it that times 2x minus 1 there. We have a 3 squared and then a 3 to the 2x minus 1. So notice a difference here. I took this base, I changed the base, so that's going to be a power rule. This is 2 different bases, so we're going to add those, okay, for those two. So it's going to be 3 to the 6x minus 3 equals 3 to the 2x plus 1, because negative 1 plus 2. And now we're ready to solve these ones. Minus 2x plus 3 plus 3. We get 4x equals 4, so x is 1. Okay. So, I mean, those take some work. You have to have some exponent skills. Remember your exponent rules. A lot of those things is what I was saying. Keep harping on. You need to practice those. But now as we get into the parts where we run into the brick wall, or the what do I do now, of 2x equals 50, right? Because there's no way I could get 50 into a base of 2. That's where we run into trouble. So that's your first problem. There's trouble because 50 can't have base of 2. Okay? Now determine, by considering powers of 2 integers between which the solutions must lie. We can estimate where it's going to be between, right? And how can we do that? Well, we know that 2 to the 5th equals 32, and then 2 to the 6th equals 64. It has to be between 5 and 6 then, right? If 2 to the 5th is 32 and 2 to the 6th is 64, we expect our answer to be between there. So if we estimated, estimation is 5.6, okay, that's fine. You can do that. Okay, but now we're going to show a little bit more algebra way of doing this, in which I actually really appreciate. I like this because when you're doing algebra, we know to undo things is how we solve. And right now, the biggest issue when you're seeing this is that there's an x in the exponent. We don't know what to do with that. How do we get that? How do we get that down? Well, this is where we use logs. So here's the work. Just like we can divide both sides, just like we can multiply both sides, we can log both sides. Okay, so I simply put a log to 2x and a log to 50. Now we're saying, well, how does that help you? Because the power rule, or power law, excuse me. Rules is for exponents, laws are for logarithms. Okay, power law says I can do what? Move this down. Now what? Divide it, yep. Divide log 2, divide log 2. We just solved for x. Because that was within the log. That was, you're talking about this number.
Because these are 2 separate.
This is x times log 2, so I'm dividing the whole log.
Okay.
Yeah. Yeah. Now, you may be saying, but we know this, Mr. Baker, because, if I wrote this in log form, maybe log base 2 of 50 equals x, right? And we know change of base gets us here. That's correct. Change of base will get you this answer. But as we get into harder problems, we want to log both sides. So we're showing you the basic for doing this operation, but you're right. If you use just change of base from here, like writing this in log form, you can do change of base, of course, and you see you get the same thing. right? Okay, so it's just kind of proving that you can log both sides, which I think is kind of neat, but I'm also a math teacher, so. Okay, all right, so let's look at the first example here, and this definitely just kind of got everybody kind of last class like, whoa boy. Okay, so what I'm going to do is I'm going to do A and C, and you're going to try B and D. I'm going to pause the video. A and B are a little bit easier. C and D are they're more difficult. Exact form is that instead of actually calculating when we have that situation, we leave it. Okay, so that's just so you don't get the decimals. So when it says exact, that's what they're saying. And then we're also going to go ahead and calculate it. So the first one here, we're just going to do that easy practice here. We're going to log both sides. And the x drops, and then we divide the log 4. It's very simple to what we just did. So this right here is your exact form, part 1. And then part 2 says to do the decimal, and the decimal for the first one, if you calculate this in your calculator, you get 1.792. Okay, and I did this last class, so I think what I'm going to do is I'm going to tell you to just watch for part C. I'm going to run into a dead end, and I'm going to show you why we're going to do things differently so we don't get to the dead end. So if you don't want to write the dead end down or the part where, like, what do we do now, just watch, and then we'll go through it, okay? Last class, they were mad because they wrote it all and didn't have room, so it's up to you, okay? All right, so let's look at this one real quick. All right, so we're still going to log both sides, but the trick here is there's x's in the top for both of them, right? So what we're going to do is we're going to log both sides. So log 6 to the 3x equals log 3 to the 2x minus 1. We're still going to drop. Okay. Oops, didn't drop. Important to have brackets there because it's that whole exponent together, and then log 3. Now here's what is kind of the dead end part a little bit. So what you can maybe think is I want to get my x's together, right? So if you get your x's together, you would divide the log 6 over, and then you divide the 2x minus 1 over. So this would just kind of go under here, and then this would go under here. They kind of just switch spots. Okay? So it would look like this. This is a dead end. Does anybody want to take a guess, or maybe they can see, why is that a dead end? Good, the x's aren't by themselves. The x's are on the same side, but the problem is that I kind of have a situation where I have two x's, right? That makes things difficult. The other thing that's difficult is that a lot of people are like, oh, can we just cancel these? Never. I've been mad about that all year. Don't do that, okay? But the other thing, this is the problem, to tell you. That's the dead end piece. That minus 1 is kind of enabling us to do what we want to do, okay? Or disabling? I don't know. Anyway, it's not allowing us to do what we want, okay? And so what we're going to do is we're going to scratch this. I will erase it to right here, okay? And so what we're going to do is I'm actually going to distribute this. Okay, so we're going to write 3x log 6, 2x log 3, minus log 3. So the negative 1 to the log 3. Do you see that? So the 2x hit the log 3, the negative 1 hit the log 3. Now, for those of you that have aspirations going to calculus, you will do this type of algebra move a lot in calculus to isolate variables. Okay? So what we've done is we separated them because what's neat is, and what you need to realize, you need to visualize a log 3. That's a number. Log 3 is a value, right? I can put log 3 in my calculator and see what that is. Okay? But this, we don't know what it is. So we're going to get our x's together now. We're going to minus this over. Now, can anybody tell me why that's going to help us? X log 6 over 3. Oh, nope, close. I see what you're doing. Nope, won't do that. She tried to do the quotient law. What's that?
Yeah, because they have the same base, so can't you just subtract the
Yeah, but they have the stuff in front, though.
Oh, the wooden one over there.
No?
I don't know what the
That's okay. You're trying.
what you like.
Let's just get back. What's the goal right now? We're trying to isolate x. They both have an x in common. Pull it out. It's awesome. But that's neat because look, this whole thing right here, that's a value. We like values, right? Now the x is isolated, so what's our last step? We divide this chunk back over and leave the x here. Just like that. And now that's our exact value answer. And now we'll calculate that. Okay? Yep, if you want, I'll show you. This is how you want to put it in your calculator. You want to do brackets, negative log of 3, divided by bracket, and then you're going to do 3, and this will have a bracket here. They do the brackets around the log. 3 log, bracket 6, minus 2 log, bracket 3, and then bracket. That's how it should look in your calculator. Okay. All right, so I'm going to pause the video. You can calculate that. You should get negative 0.346 when you do calculate that. If you don't get that, I can help you put it in. But go ahead and try B and D now, please. Let's go over the first one. I'll give you some more time for D. Okay, so B, yeah, the first thing you should do is minus the 4. Because when we log both sides, we'd like to have it just with an exponential. So 8 to the x equals 36. Log 8 to the x, log 36. So x log 8. Okay, divide the log 8. Divide the log 8. And so then x should get you 1.723 here. Okay, so this is your exact form. Okay, here's your hint, though, to get started on D. This, okay, I saw this in a couple quizzes, 2 times 3, absolutely not. It's got an exponent, you can't do 2 times 3. Okay, so don't do that. Okay, we need to think more in the sense of that's a product. Okay, so we're going to log both sides still. Okay, but the problem is that we can't drop the x minus 2 because that 2's in the way. But it's a product, so we want to write like this. Now you can drop the x minus 2. And so this is where you guys should get. That's usually the tricky part. See if you can solve it from there. Okay. Right. Okay. So what we want to do is we can drop the x minus 2 in front of the log 3 now. So it's going to be log 2 plus x minus 2 log 3 equals x log 7. And we want to distribute that. So we have 2 log 3's. So log 2 plus x log 3 minus 2 log 3 equals x log 7. Now we did that, so now we can take this chunk with the x on it and move it over. Log 2 minus 2 log 3 equals, remember I'm minusing it, so it's going to be x log 7 minus x log 3. And see, look, this was the point. These have x's. We can now pull an x out. So you'd have log 2, log 3, x times log 7 minus log 3. And now we're to the final spot here. We're going to go ahead and divide that over. Okay, so let's divide it over here. So this is your exact answer, and this is what you're going to calculate. You want to calculate that. Okay, any questions there? When you do calculate on this one, you should get negative 1.775. didn't get that? Okay, I can take a look here. Yeah. All right, so then example 2 here is just kind of the part we've already stated about how it's essentially the change of base. So you can kind of, we'll just skim over that. But the 4 to the x1 equals 12. We know that's going to be log 4, or sorry, log 12 over log 4 when we do it, right, by the change of base. Because this would be log base 4 of 12 equals x, so log 12 over log 4. Just that idea of the simple ones, it is change of base, that's okay. Okay. Sample 3, talking about population growth. So it says according to statistics in Canada, 21st century, Canada's population has been growing at an average annual rate of 1%. The exponential equation is P naught, which is like starting amount, P naught. 1.01n can be used to predict the population P n years after knowing the population of P naught. So it tells you all this stuff here. Canadian population is beginning of 2001, so that's before 2001 starts. So it's like, we'll get to why the answer is what it is when we get there, but remember, we're counting 1. So essentially, we're starting at 0. We'll talk about that when we get there. With approximately 30 million, so that's our P naught. 30 million is our starting amount for people. Okay. They estimate the Canadian population to reach 50 million. Okay, with the same average growth. They've already told us the growth here, it's 1.01. So we have everything we need to develop this equation. So we can write 50 million and 30 million is fine. You'll see it'll go away really quickly, so don't panic about seeing all the zeros. So we know we're trying to figure out this number for 50 million. We don't know when the population is 50 million. So we're going to go 50 million equals 30 million, 1.01 to the n. And we're trying to figure out how many years. So for 30 million people now, that's the growth. How many years until we're at 50 million? So you're still going to divide the 30 million over, and that's what I'm talking about. So you're going to see that the zeros are going to go away pretty quickly, because 50 million over 30 million is simply what? 5 over 3. Yeah. 5 over 3 equals 1.01n. And so now we're into our today's stuff. We're going to log both sides, or you could write it in exponential or logarithmic form, whichever. Okay, but if we log both sides, okay, we're going to see it's going to be n equals log 5 over 3 divided by log 1.01. Okay. Okay, so we do this and we get 51.33, or 34, but the point is it's just over 51. So that means it would take 52 years to be over 50 million, right? Because we can't stop in the middle of the year. We're trying to figure out which year we'll have 50 million. Okay, so we know we're looking at essentially 52 years. So what I was trying to say was, since it's at the beginning of 2001, that means we're counting 2001. So 2001 is your first year. So essentially we're adding from 2000. So 52 from 2000 is 2052. Everyone wants to say 2053. I know. It's that same thing in Math 20. Remember that? With the geometric series? Yeah, you got to remember where you're starting what year. So it says the beginning of 2001 is where we're starting. So that's our term 1.
Okay, so that's when we have 30 million?
Right. 2001 we have 30 million. No. Sorry. Before 2001 we have 30 million. 2001, the year of 2001 is our first growth.
Okay, so that's like from the beginning of 2001 on.
Right.
No.
Nope, you're right. She said it right.
No, I mean, like, I don't know how this conversation works.
Yeah, you're right.
Every single year.
Yeah, oh, I know. It's very difficult. And so the point is that it's going to be 52 years counting the 1. So that's just going to be to 52. 1, 2, all the way to 2052. Okay? So The key word here, though, is right here. And like Maddie, you said the best. Beginning of 2001. Okay, so before we start. All right, last page here for this lesson. We'll take a break. Okay. We can take the logarithm of each side of an exponential equation, any base, but it's simpler to use a calculator base sometimes. If the base of the exponential equation is e, we know it's natural logarithm. Don't forget that. ln is base of e. Okay, so we're doing some e stuff now. So if we want to solve this one, okay, let's go and solve this one. So in general, guys, when you get an equation like this, isolate the exponent. Okay, isolate that. So I'm going to minus the 9. So 7e to the negative 2x equals 3. And I'm going to divide the 7. E to the negative 2x equals 3 over 7. And this is where we want to ln both sides. Yeah. What makes me want to ln, okay, what makes me want to ln or natural log is the base of e. When you see that base of e, we want to use the ln. Okay? Because what happens here, it's actually it's cleaner, it's actually nicer. Because if I ln this and I ln this, that drops. What's ln of e? You should know this. It's just 1. It's ln of e is 1. It's gone. Okay, review for you guys. You're scaring me right now. Log base e equals ln. So if I go log base e of e, we know that's 1. That's what this is. That's log base e of e. Okay? ln is shorthand for log base e. Right, so now it's just negative 2x equals ln of 3 over 7. And we now always divide negative 2 to that value. This is a value, right? So we take this value, we divide it by negative 2. That's your exact value. Okay, and you should get, when you calculate that, 0.424. So go ahead and check that. We're going to talk about one more thing. Use your calculator for it. You're familiar with this method. It's no different than parabolas, but we'll talk about it in a second. Yeah, sorry, handwriting. 3 divided by 7. Okay. Any questions on that? The last one there, the ln. So remember, ln, when you see e's, use ln's. That's your trigger. When you see e's, use ln's. That will also come up with calc. Okay, so if you guys are familiar with this, I'm going to summarize this because intersect method is when the graphs cross, you're going to find the intersect for their solution. And then the zero method is when you're going to make if you have two equal equations, you're going to subtract them to one side and now find the zero because nothing's over there. They both give you the same answer. So it doesn't matter which one you use. So, for example, I'll just explain this one. For the x equals 7, if I want to intersect, I put this in y1, I put this in y2, and I find where they cross. So the picture that I just kind of roughly have would be through 7, and then it's going like this, and it's an intersect. Okay, and you're going to find that answer using the intersect in your calculator. Does anybody want to see that again with the calculator? Second trace, I think, is number 5. Is intersect. Okay. Intersect's the easy one. You just hit enter 3 times. It'll get it for you. Okay. Okay. Now, the zero method, what do I have to do to the zero method? I would minus the 7 over, and I'd just put that in y1, and I'd do the zero function, second trace 0, and I'd find the 0. That's the difference. And so that one would look like something like this, and you'd be finding that value. Okay? Okay. Okay, I'm going to pause the video. That's all we need for this, but I'll take questions.